So what can we do with all of this? We can convert from a triple bond to a double bond to a single bond, alkyne, alkene, alkane. We can go to an alkyl halide. We can go from the alkene to the alkyl halide. We can go from the alkene to the alcohol, from the alcohol to the alkyl halide. From an alcohol we can make carbonyl, and from the carbonyl we can do all the neat stuff from this section. So most of the previous is stuff from before this section, and here we're just going on from there with what we can do. Okay, so think about these reactions as you're going along. They're very important that you understand what is possible in this, and you see the strategy. So is there a change in the number of carbons? Is there a change in the functional group? The two things you need to think about as you work problems in this section, in this class, as we're going along, as we go towards the end of the semester. So here we are continuing on in aldehydes and ketones, and actually in this video you've watched a few of the reactions already in the review for aldehydes and ketones, but we have the Grignard. Remember, it's just a CH3 minus MgBr plus, reacts as if you had a full anion there. It's not completely ionic, but it does that. Then, so all three of these, well, the top two are just a nucleophile adding to the carbonyl, and then you protonate the OH. The bottom one, the Wittig, is the addition of the, you have the carbon with a negative, phosphorus with a positive, the carbon adds to the carbonyl and all of that. So we can add a carbon chain, just a plain alkyl chain on there. We can add a nitrile on, we can cleave the nitrile, we can reduce the nitrile, so we can have functionalize that chain we add on there, or we can make an alkene. These are the three main carbon-carbon bond forming reactions we can do now that we're in the section 3, what we can add to a carbonyl. We can also oxidize a ketone up to the ester, just like we've shown with the peracid. So spectroscopy, what do we remember about IR and NMR from Word 1? IR, the aldehyde, shows up roughly about 1720 in the IR, and it also has the aldehyde peaks at 27 and 2850. Those are the two that are most helpful for an aldehyde. Then the proton NMR and aldehyde shows up between 9 and 10. The aldehyde hydrogen, that hydrogen on the carbonyl shows up between 9 and 10, whereas the hydrogen on the carbon next to the carbonyl shows up between 2 and 2.7. So depending on where the signal is, we know what kind of environment it is, and we can use that. And then in the carbon-13 NMR, we know that the carbonyl carbon shows up somewhere around 200 parts per million in the C13. Okay, so we have to remember what kind of spectra are we looking at. Is it IR? Are we looking at the stretches of the functional groups? Are we looking at a proton NMR signal where we can tell what kind of environment the proton is around? Or are we looking at the C13 where we are looking at what kind of carbon is it? Where could that carbon be? Hey, now here, I know the first thing you're thinking is, dang, there's a lot of reactions. But they all do the same thing, so don't think there's 50 different reactions. They're all very similar in what they can do, so keep it simple as you're going along in these. Okay, so we can make the acetal or ketal, the hydrate, we can do the Wittig, we can add, oh, got a mistake there, we can add the nitrile, CN minus, the cyanide, we can add the Grignard, we can add a hydrogen, okay, in these on the side. Those are just a strong nucleophile that adds in. We can make the hydrazone. We can cleave the hydrazone with hydroxide to make the alkane. We can do this directly also from the carbonyl with just hydrazine and hydroxide and heat. We don't have to form the hydrazone and purify it. We can make the oxime, we can make the ester cyclic or acyclic, we can make an enamine, we can make an imine, and we can make the dithiene. And the dithiene we can reduce to the alkane. So as you're going along, think about all of these reactions and what you can do with them and what happens with them. Okay, you should be able to draw the mechanism for all of the inside the circle reactions with no problem. Okay, if you have any problems with any of those, feel free to ask as we're going along in class or send me an email, but you should be able to draw. They're all roughly the same in what happens. So here's a few mechanisms to practice. We protonate the carbonyl, then methanol adds in, then we remove the extra hydrogen off of the hemiacetal with an extra methanol, because methanol is the solvent, so we have it around, so we can do that. Okay, with methoxide, we have a strong nucleophile. It adds in, forms the O- and the OMe, and then that O- is going to go grab a hydrogen off of acid in the second step to give us our answer. In the bottom one, the first couple of steps are going to be exactly the same. We're going to take the carbonyl, we're going to protonate it, we're going to add methanol in, add methanol in, so we're going to get the OH and OMeH. We're going to remove the extra hydrogen to get to the neutral hemiacetal like we did above. Then we're going to protonate the OH. To make the good leaving group, reform the carbonyl equivalent, kicking out the leaving group, so that gets us the double bond to the oxygen with the methyl on it, and then another equivalent of methanol adds in to break the double bond, give us the OMe, give us the OMe and the OMe with the H on it, and then another equivalent of methanol will come grab the extra hydrogen to form the acetal or ketal, depending on did we start with a ketone or an aldehyde in the reaction. Okay. Then we have the Wittig, where the butyllithium grabs a hydrogen off to form the negative charge on the carbon. Then that can add to the carbonyl, break the CO double bond, which is going to give us the CpCO minus plus. The carbon with the phosphorus has a phenyl ring off of it and a hydrogen. The phosphorus has the 3 phenols. The oxygen was connected to a carbon with a methyl and a hydrogen. You're going to form the 4-membered ring, so we form the oxophosphatane. And then the oxygen carbon bond breaks going towards the carbon, the carbon phosphorus bond breaks going towards the oxygen carbon bond breaks going towards the oxygen, the carbon phosphorus bond breaks going towards the carbon because of electronegativity to give us our alkene, along with the dreaded triphenylphosphine oxide that we have to purify away from our alkene as the reaction finishes, when the reaction finishes. And here we have the reduction of a carbonyl with hydrazine and hydroxide. So, and we have drawn this before, but we'll show it again. We've drawn all of these before. We're going to remove a hydrogen off of the hydrazine. The hydrazine adds to the carbonyl. Oops, one's a methyl. Oops, no H, sorry. Got ahead of myself. O minus, and then we have the one hydrogen on there. We need to protonate the OH off of water, so we can grab a hydrogen off of water to get to the NNHCH3OH. Then we can remove the hydrogen off of that, and I'm going to run out of room here real quick, so I will have to draw on to the next page. N minus methyl OH H. And then from here, since we're in heat, we can make the OH leave, forming the double bond out to the nitrogen. Okay, so I'm going to draw the next product on the product of this step on the next page, but I'll let it sit here for a second so you can look at it without me going on too quickly. So what we can do from here is, when we form the carbon-nitrogen double bond kicking off the oxygen, on the next page, add a page here, we have the carbon, the hydrogen, the double bond to the nitrogen with the NH2 off of it. Then our hydroxide is going to remove an extra hydrogen, or remove a hydrogen off of that to give us the N with a negative charge and a hydrogen. We can draw the resonance structure of this, putting the negative on the carbon with a double bond out to the NH. This can go grab a hydrogen off of water, hydrazine, it doesn't matter where it comes from, to give us the double bond to the N, double bond between the ends, with now two hydrogens on that carbon. Hydroxide, or the anion of hydrazine, can remove the hydrogen off of that to give us an N, double bond N, lone pair, that can go down to form a double bond, send the electrons to the carbon to give us nitrogen gas along with the anion, and then that anion can go grab a hydrogen off of water, off of hydrazine, to form, in this case, ethane, but it doesn't matter what it is. What's off of the carbonyl carbon, that part doesn't change in any part of this mechanism. And that gets us to the ethane for there. And yes, this is a longer mechanism, but you have to be careful what's going on as you're doing the mechanism. Make sure you follow along with what's possible.